All right, Mr. Reporter.
Questions or other questions?
Number 4 on master set 32.
Mr. Dawson, I was gonna ask that.
So I'm just dumb.
I couldn't figure it out either.
So A,
All of it. Sorry.
it's just A and B, right?
Yeah.
Okay. So the question, the first question, I have my solutions, I don't have the actual question. The first part is find the EMF, the induced EMF.
Mhm.
What is the induced EMF equal to?
I guess the resistance times the current. I mean,
Okay, well,
The change in magnetic flux over change in time, well, the negative change in magnetic flux over change in time.
it's also, if you wanted to take it that next step, it's also integral of B dot D S, D R, whatever letter you have to be using. This relates to that other question that you had.
Oh, I didn't know that. Okay, well, that kind of helps me think.
Yeah, Faraday's law. Faraday-Lentz's law. So we need to figure out what is phi of B in order to take the derivative. And so that is integral of B dot dA. So this is, it was a line of current and then some rectangle above it. Well, I went through a problem to figure out what B was with, I think, a constant current, didn't I?
yeah, I think it was an infinite line.
Do you want the master set? I have it right here.
Yeah, that might make life a little bit easier. All right, so we have a current, which is 5 amperes times the cosine of 0.7 radians per second. So that's my current. And I give a resistance. Thank you. So I know that the magnetic field here is induced by the current. I have a long wire here, so I know that B is equal to U naught I over 2 pi R. I guess that's the magnitude of B.
How did you, I guess, whenever you derived that, I remember it was for an infinite line. How do you, like, do we just assume that it's infinite based on the dimensions, or?
Yeah.
Okay.
How long did I make the wire that's carrying the current?
A wire.
A wire. Okay.
Yeah, it is a wire.
Yeah, the assumption was that it is incredibly long
Okay.
compared to the size of the rectangle.
A wire A is running.
Along the positive Y, or along the Y-axis?
Yeah.
Okay, so
Yes,
it's
Y-axis really long. Despite, in math, you know, they get lazy and they just write only part of it and they go, that's good enough. It's like they're becoming physicists. All right, so we have the infinite wire approximation here. And so my area, well, in essence, I know that the magnetic field is going to be the same everywhere along this infinitesimally small path here. That is some distance r, but the width of this little segment right here is dr. So I'm doing an area. So first off, my area vector is either pointing that way or that way. it's gotta be, the area vector is perpendicular to the surface. My magnetic field, well, if my current is running in this direction, what's the direction of my magnetic field?
Towards us.
Yeah, out of the
Okay.
page from the top.
So I'm just basically gonna solve that problem. If I changes to the other direction, well, I'll get a negative, but I'm just going to have these two in the exact same direction, just, or parallel or anti-parallel, but that'll show up here with like IN. So this is just the integral of BdA, which is the integral of u naught I over 2 pi r. And then dA is whatever that width is, times dr.
The width is 0.03, right?
Yeah, it sounds familiar.
It is.
Pull the constants out. So I got u naught over 2 pi w, and left with I over r dr. Well, I's not constant, so that can pull out. Sorry, we can make that substitution. So I've got this I sub naught, so pull that out, so I got u naught w over 2 pi times I sub 0, which is 5 halves, times the integral of cosine of omega t for r dr. The trouble is, though, that, well, not trouble, the nice thing about this is that cosine of omega t is not dependent upon r at all.
So we pulled out.
So it does pull out.
Yeah.
And so what you're left with is a bunch of constants times the integral of dr over r.
And then, is the intervals for that integral, from 0 to whatever the max distance it could be?
The smallest distance r can be is that distance right there, which I think was 0.06.
Yeah, it
Yes.
is.
And then the longest would be 0.09, so it'd be 0.06 to 0.09. So that will get you phi sub b. And then you take the derivative with respect to time, and then you plug into here. So that is this whole thing here. I just didn't bother writing the stuff in front. And there's a time dependency, and this is where the time dependency comes in.
And then now that you have, so that is the derivative of the magnetic flux? That's,
Yes.
okay, so, is that just the equation inside the integral? Does the derivative cancel out the integral?
Did the derivative cancel?
Am I thinking of it?
No,
correctly?
because this integral is with respect to the distance. This derivative is with respect to time.
Okay.
So they're looking at two different variables there.
Okay. So then once you find the flux, you take the derivative of the flux?
Yes.
Okay.
Why did you use cosine?
Why not? It's oscillating back and forth. I just decided
Oh, so
to.
that doesn't impact it?
It will impact it when you do the derivative. So this will end up being some number. All of this is just some number. So ultimately, you're gonna end up with some number, which I'll just label as that, times the cosine of omega t. This is going to be my magnetic flux. When I take the derivative with respect to time, then I get the n omega negative phi dt. I get negative sine omega t. So I'll end up with a sine in my final answer. I'm sorry. The original problem, it was signed, should be signed, not cosigned.
Yeah, that's what I was.
Yeah, okay, sorry about that.
Oh, okay, I thought,
Yeah.
I didn't know there was a reason why you used cosine.
No, just, I'm old.
Sine.
And then when it talks about how the square can be positioned so that,
The induced current is zero?
yeah. I just don't, and I know that's like supposed to be a conceptual thing, but
Yep.
I don't even know where to start with that.
Alright, so what's causing there to be an induced current?
The magnetic field.
More than that.
Oh,
Magnetic
the
flux.
movement, the change in the electric flux, right?
Or magnetic flux.
Magnetic flux, not that.
So we have to orient it so that the change in the magnetic flux is zero. How does that happen?
Make the areas zero?
Alright, Chance, what'd you say?
Can you just flip it down, so,
Flip it. Well, it depends on how you flip it. Yes, you are gonna flip it, you're gonna reorient it.
just,
You mean like perpendicular?
So,
yeah,
like that, or like that,
like that.
like that. It depends on how you orient it, but if I got a magnetic flux that's floating around this thing, so if I look at it head on, so there's my wire, I got a magnetic flux that's, we'll just assume going in that direction at the moment. I can orient it so that whatever flux comes in, comes out.
So, yeah, you put it like horizontally at the top, right?
Yeah, so just be careful about the wording there. So if I put it like that,
Yeah, cause it would come in, but then it would come out. right?
yeah,
Okay, so.
so that it's centered over the wire.
Mhm.
So that's why, if I just flipped it like that, it depends on what
Okay.
is
if
meant
it's
by the hand
centered or
gesture.
not, okay.
That is a solution, there's
Mhm.
another one that some people came up with too.
So technically, when you orientate it like that, it's technically parallel to the magnetic field?
No, it's not parallel to the magnetic field,
Or is it just more that the magnetic field goes through it, goes in
It-
and
it'll
out?
go-
Yeah,
come in and out.
It goes in and out, so it
Okay.
cancels itself.
because of symmetry. It's also possible to orient it so the magnetic field doesn't go through the surface at all.
Is it, yeah, if you, so from the view on the right, if you have it so that we see the square, is there anything that goes through it?
Oh, yeah, so if you did that,
Yeah.
then nothing would go through it.
And that equals zero?
Yeah.
Okay.
So I did it the hard way, where you could just.
That-
like that.
What Chance suggested was was the way that I envisioned it, and that some student came up with, that going the other way, and I go, oh, yeah, of course.
So you want it, so in this case, you would want it oriented along K? Because the magnetic field points towards this?
You say along K, this one, okay, what do you mean by that?
Along
This was X, wait, X. That was Y, X,
then K,
K would be into the board, given this orientation. Or C. So if you orient it parallel to the XZ plane.
the
that would do it.
XZ plane.
Yep.
Wait, parallel?
Parallel to the XZ plane, because the XZ plane is this way. So if I orient it that way,
Uh-huh.
that was Pat's suggestion, or Chance's suggestion was to basically shift it so that it's over, so that the middle of it, whichever middle you want, the middle of it, is right over the Y-axis.
Oh, okay. So that technically works?
Yeah.
XZ? Because it would go like that?
Yeah, there's no Robin Hood split in the side of the pane. The pane, that frame there is infinitesimally thin, so magnetic field lines would just go beside it, it wouldn't actually penetrate.
Oh, because it's so thin?
Yeah.
Ah.
I also had a question on, number 5B.
Yeah.
Now it's time to give me those knucks.
Are you gonna ask about that?
They can
Is
read each
it-
other's mind.
Is it moving initially? Or
No,
is
it
just-
doesn't move to part C.
So I don't understand how there would be a current.
What would the current be?
0?
You just figured it out, James.
Over get units.
I had the exact same question.
I just said there'd be no current. Is that fine?
Yeah, I always, whenever I see someone write, it would be 0 and then none. You know, like waffle back and forth on that one. There have been times where I have marked off for no current with a philosophy that it's like, is no slope and zero slope the same thing?
No.
No. Does that work across the board? Depends on my mood.
I guess it depends on what you're talking about.
Or if you like the student or
Right.
not.
Uh-huh. Like having 0 burritos is the same thing as having no burritos.
Yeah, better put 0.
Amperes. I probably should settle up on one answer for that, but, I haven't yet. At the rate I'm going, I'll die before I figure it out.
So we say the current is 0 amps and therefore it doesn't have a direction?
Yeah, if you just say 0 amps, then I'm good with that, there's no
So
direction.
I don't have to, okay.
The rest of that problem, I remember we went over, it was like the U and, the U-shaped wire, I believe, with the wire that can move freely, and we solved it using those methods, whatever we did over that one Zoom call.
Right, so, wait, what's your question again?
We can use, we derived, let me find the formula, the EMF equals the magnetic field times the width times the velocity, sorry,
The BLEV?
the speed, yeah.
The BLEV formula assumes that the movable wire is moving at a constant velocity, and the magnetic field is constant. Those were the assumptions we went into when we made that.
Okay, yeah,
So if the wire is not changing if the wire has a non-zero acceleration and the magnetic field is changing, then I would recommend some calculus at some point.
Okay. I have a conceptual question. So
Okay.
when you do have the U-shaped wire with the wire that can move
Right.
to change the flux, when the flux is decreasing, then the magnetic field that the wire produces, that'd be in the same direction as the magnetic field it's in,
Yes.
but when it's increasing, it's the opposite direction.
Right.
Okay, so, okay, thank you.
Other questions?
And it doesn't really matter if the current's going in or out of the page.
You say into or out of the page,
The magnetic field.
no, the generalization that you said is true whether magnetic field's going in or out. It will affect which way the current flows.
Yeah, but yeah, it'd just be the opposite if it's increasing,
Correct.
and the same if it's decreasing. Thank you.
So for 3, you only pay attention to the components that actually affect the force.
You said for 3?
Yeah, well, yeah, Master Set 3, the one we were just talking about.
Sorry, talking problem 3 from Master Set 32.
Yeah.
What was the question again?
So you only pay attention to the components that would be affecting the current. You kind of just ignore like the other component. Is that right?
Which components are you planning to ignore?
Well, like, I don't know. I'm a little confused.
So on 3, you've got the magnetic flux is shrinking. So as Chance would say, the induced current would produce a magnetic field that will try to keep it from shrinking. I feel like I'm missing your question completely here, so I'll try again.
Like the sides parallel running in the y-axis, does that affect anything? I don't know. I'm just kinda confused, like which components affect the current.
Alright, so the change, alright, so the EMF that's induced, that will produce the current, the induced current, is equal to negative change in the flux. So the things that we care about are things that are changing the flux. Well, going more formally out there, my flux is the integral of V dot dA. So the only things that can affect the EMF is the magnetic field changing, is the area changing. Those are the two things,
Oh, I have the wrong formula.
with respect to time.
Okay. I have the wrong formula here.
But ultimately, in this case, magnetic field is constant. Area vector is changing at a constant rate. So this can be done without calculus. This is just, I wrote a formality up here to try to cover every case.
Well, number 2, are you talking like at that instantaneous point in time when the magnetic field's shrinking?
Yeah, so the magnetic field is getting smaller, and